In this tutorial, we will be discussing Raoult's law in two-component systems. Adding a solute to a solvent modifies the properties of the pure solvent. These changes in pure solvent properties are referred to as colligative properties. Colligative properties depend only on the number of solute particles relative to the solvent particles in the solution, not the type or kind of solute particles. Raoult's law compares the pressure of solution to vapor pressure of a pure solvent. Vapor pressure of water over a solution depends on the number of water molecules per solute molecule. For instance, down here in this picture, we have pure water. This is in dynamic equilibrium, meaning that the amount of molecules that are going from liquid to gas are the same as the amount of molecules going from gas to liquid. Once we add a solute to it, more molecules are being pulled and held down. So the molecules are the same going from the gas to the liquid, but fewer molecules are escaping back into a gas because they're getting held together in the liquid form. Now, mathematically speaking, because mole fraction of a solvent, chi of A, is always less than 1, the vapor pressure of a solvent over a solution is always lowered. The vapor pressure of a solution is given by Raoult's law, which is the pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent if it was a pure system. In a two-component system where both the solute and solvent are volatile, the change in pressure, the change of vapor pressure of a solution is the mole fraction of the solute times the vapor pressure of a pure solvent. Note the lowering of the vapor pressure is directly proportional to the solute's mole fraction. Vapor pressure of a volatile solvent over a solution is given by the mathematical equation. The pressure is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. The vapor pressure of the volatile solute over the solution is given by the relationship of the pressure of the solute is equal to the mole fraction of the solute times the vapor pressure of the pure solute. These things added together will give you the pressure of the overall system. An ideal solution is one that follows Raoult's law at all concentration for both the solute and the solvent. So if we look at this chart here, we have chi of A, meaning that's the mole fraction of A, and if it's at the very beginning, that means there's no solute in there. However, as the solute increases to maybe up to 100%, the vapor pressure increases. So the more A you have, the vapor pressure of A increases. At 100% B, which is here where there's no A, the vapor pressure is up here. But as you add more A, the vapor pressure decreases. So with a two-component system where A is the solvent and B is the solute, you have a vapor pressure lowering. This here, the vapor pressure of the solution, are those two graphs added together. The vapor pressure lowering is proportional to the mole fraction of the solute. Let's try to put this one in practice and do a practice problem. Determine the mole fraction composition. So the question is asking for the chi of the solute and the chi of the solvent. The mixture of the solution is composed of two volatile components, pentane and hexane. The solution's vapor pressures are 258 for the solution, 425 torr for pentane, and 151 torr for hexane. Assume ideal behavior and that the mixture is at room temperature. Alright, so when we're thinking about this, first thing we're going to do is look at them separately. the pressure of the solute and the pressure of the solvent. If we want to figure out the total pressure, we want to figure out these components and add them together. So the pressure of the pentane, the mole fraction of the pentane, and the pure pressure. The pressure of just the hexane would be the mole fraction of the hexane and the vapor pressure of pure hexane. So let's take a go at this. The pressure of the solution is equal to the mole fraction of the pentane times the vapor pressure of pure pentane and the mole fraction of the hexane times the vapor pressure of pure hexane. From our problem, we can get these numbers. The solution is 258 torr when they're added together. The pressure of pure pentane was 425 torr. And the pressure, then we have the mole fraction of hexane, and the pressure of pure hexane is 151 torr. Alright, the problem here is that we have two variables in the same problem. We can actually reduce this and make our lives easier by simply saying that the chi of the pentane and the chi of the hexane, these are both fractions, and as it ends up, they'll be equal to 1 because 100% of the solution. So if we take 100% of the solution, some percentage of it's going to be pentane, some percentage of it's going to be hexane, and we add it together, and it's going to be the whole solution. So that's where we can get away with this. So let's solve for hexane here. So the chi of hexane is equal to 1 minus the chi of pentane. Now we can show that chi of hexane is here, which means since that is equal to 1 minus pentane, I'm going to put it into that equation. $425 torr times chi of pentane plus 151 torr, and I'm going to throw in 1 minus chi of pentane here instead of hexane. Now I can distribute that 151 to both of those. I'm going to start leaving out the torr just for simplicity's sake. They're all the same unit, so it's okay. I'm distributing out the 151. Alright, now that we have just one variable, we can start reducing this. So let's subtract 151 from both sides. That comes out to be 107 on the left. And we can combine the negative 151 and 425 to be 274 chi pentane. Alright, let's go to another sheet. 107 is equal to 274 times the chi of pentane. We need the chi of pentane all by itself. 274 by dividing both sides by 274. So 107 divided by 274 is 0.391. So that is our first answer. They wanted the chi of the solute and the chi of the solvent. We solved for pentane, which was the solute. Now let's get the other one. We said before that chi of pentane and the chi of hexane are going to add together to equal 1. So 0.391 is plus the chi of hexane is equal to 1. Subtract both sides, and you get 0.609. Those were for ideal solutions. For ideal solutions, solute-solvent interactions are equal to the sum of the broken solute-solute and solvent-solvent interactions. Ideal solutions follow Raoult's law. Effectively, the solute is diluting the solvent. If the solute-solvent interactions are stronger or weaker than the broken interactions, the solution is no longer ideal. When the solute-solvent interactions are stronger than the solute-solute plus the solvent-solvent, the total vapor pressure of the solution will be less than the predicted Raoult's law. That's because you're trying to hold on to them even more. The solute-solvent interactions are stronger and therefore less molecules are escaping. The vapor pressure of the solute and solvent are lower than ideal. When the solute-solvent interactions are weaker than the solute-solute plus solvent-solvent that were broken, the total vapor pressure of the solution will actually be larger than predicted. And that's because there's not as much holding it together, and they don't want to be around each other as well, and so they're more going from liquid to gas more readily. And that is vapor pressure, Raoult's law, for two-component systems.